Well, hi, everybody. My name's Lassie Freeman, and I work with Patrick Cozzi, who is the co-chair of the MSF 3D Asset and Interops Working Group through the Metaverse Standards Forum. Welcome today. We're so happy that you joined. This is part 3 of a series. This is the third Gaussian Splats town hall that we've had. Hopefully, many of you were at part 1 and part 2. I think you're in for a treat today. We're delighted to have some really amazing speakers that you're going to enjoy and learn from. And we also hope to continue the discussion on our Discord channel, which I popped into the chat. Lisa, you might want to copy and paste it again for people that have recently joined. We'd love for you to continue that conversation. There's a lot of Q&A that will be happening. There's also Q&A that will happen here. Would you go to the first slide, please, Lisa, or move forward? Neil, can I lean on you to give the intro and talk a little with these intro slides, if you would? Patrick is traveling, and I'm afraid that he's gotten caught up and is not able to join us right now, but hopefully we'll pop on later.
Sure, of course, yeah. We'll make it quick so get to the good stuff. So, so for those who are not familiar with the forum, we're an organization that's easy to join and very inclusive, and we're working to encourage interoperability around the metaverse, spatial computing, the spatial web. We're not a standards organization, but we get involved in pre-standardization activities like creating use cases and requirements that get fed into standards developing organizations, and post-standardization activities like testing standards once they're shipping. Are they interoperable? Are they really solving the problems that the industry needs? We're very member driven, and so if this is a domain that's interesting to you, please consider joining. Next slide. I don't know how many slides I have, but keep going. I'll keep talking. Next slide. Yeah. Oh, so we've been having this series of town halls for Gaussian Splats because it's an interesting question. No, is it the right time to do standardization? It's very possible to try to do standards too early when things are still in research, and any attempted standards will quickly become outdated. And of course, it's also possible to do standards too late when fragmentation has already occurred. So the recurring theme through all of the town halls has been, what standards do we need around neural radiance technologies, and is it the right time? And I'm really looking forward to today because we have some of the leading research folks who can help give us insight as to whether our timing is right for standardization for splats. Next slide. Yeah, go ahead.
A recap of the Gaussian Splats Town Hall 1, where really noticed a lot of interest in Gaussian Splats and thought this was a space that we should definitely engage in. And much to our surprise, we had over 450 attendees. So obviously we'd hit a nerve. It was something that the community is definitely interested in. And so we began continuing the conversation. And so what you're seeing is a part of that series. You can move forward. Lisa, we had over 16 organizations, back to part 1, So we had over 16 organizations that were represented at the GSplat Town Hall 1. Town Hall 2, we narrowed down about a couple of months later, and we narrowed that down in kind of zooming in on a more focused deep dive into GSplats and the role in shaping digital reconstruction, as you can read. And then this third town hall is to get engaged in research. And so here we are. Without further ado, since we're running a little bit late, I'm going to hand it over to Shannon Woods and Alexey Medvedev.
Hey, everybody. I'm Shannon Woods. I'm a technical program manager at Nvidia, and I have been fortunate enough to get to talk with a bunch of researchers and find out more about what they have to tell us about what's going on in the field of Gaussian splats. Several of them we have lined up to speak here today. So we have Christoph Lassner, who's a co-founder at World Labs, will be speaking about dynamic Gaussians, and I believe talking about the very new Forge renderer that just got released. My colleague at Nvidia, Zian Wang, who's a research scientist, will be talking about materials, lighting, relighting with respect to Gaussians. Then we have Wieland Morgenstern, who's a research associate with Fraunhofer, and he will be talking about compression for 3D Gaussian splats. And then rounding us out and kind of continuing on some of the topics from the earlier town halls, Projit from Niantic and Jason from Cesium will be tag teaming on our final presentation about SPZ, compression, and glTF.
Yeah, hi, my name is Alexey Medvedev. I'm a AR Tech Lead at Meta, and I am a chair of 3D Formats Working Group at Kronos. I will help with the Q&A session for these presentations. Please use Discord or Q&A in Zoom to ask your questions. I will do my job to do like a grooming and providing the questions to the presenters. And I'm really excited to hear what's coming next. And I think, so our first presenter is Christoph.
Here we go. All right. Thanks a lot for having us. My name is Christoph Lassner. I'm joined today by Andreas Sandquist, who is the lead on our Forge renderer, and talking a little bit about dynamic 3D Gaussians with our Forge renderer. At World Labs, we are building next generation models for 3D models and also like the rendering systems that are needed to create those. As part of that, we just released this renderer this Monday. It includes capabilities for efficient rendering, editing, and dynamics. In this presentation, we'll specifically talk about how we think about dynamics with 3D Gaussian splats and explain how this informed our design of the renderer. We just learned that there is a name conflict with another renderer, so we will rename this in the next few days, so stay tuned. With that, let's dive right in into a video showcasing a little bit what this can do.
So we're just going to show a bunch of clips of interesting things. This is a WebXR demo we actually developed while we're developing Forge. You can see there's quite a lot of dynamics going on there, as well as a little bit of kind of like real-time lighting stuff. A little bit of 4D Gaussian splatting here, like a little hint at what we can do. And I'm going to shut up now. You can read all the features of Forge down there. And we'll be doing some live demos of this stuff towards the end of this presentation. So yeah, I'd love to talk more about how we achieve these effects.
All right. So let's have a quick look on how we can pull this off. Oh, sorry. Let's have a quick look at the features that this has. Forge integrates completely with the 3JS rendering pipeline. This means that it works across almost all online devices, targeting more than 95% of it, because we use only WebGL2 features. So anything that supports WebGL2 or newer will be able to run this renderer. We support all current major splat file formats, including PLY, compressed PLY, SPZ, Splat, K-Splat. Also very excited to learn more in the presentations like later today, again, about the different directions that are currently happening for compression. the renderer can render multiple viewpoints simultaneously, which is an interesting feature for splats that is not trivial to implement, and we'll also show how we thought about this. It is fully dynamic, so each splat can be transformed and edited for animation. Real-time splat color editing and displacement is possible, and even dynamic creation and editing of splats on the GPU is possible thanks to a shader graph system. So now let's have a look at how this works. Let's have a look at splats directly coming into the render. So we assume those are classically parameterized. We have the position, covariance, spherical harmonics, or direct color for those. The main thing that has to happen first before we can render them is that they need to be sorted with respect to the camera from the viewpoint that they're visible from. And then they can run through the classic rest of the render pipeline to actually get them splatted on screen and then colored. Now, if we do this for one object, this is standard, like well known. If we need to do this for multiple objects, we basically recreate that pipeline, and we can just like keep going for even more, with the problem that all of these steps have to be run through for every single object, and even after they're done, blending them is not trivial. For example, we have this logo on the top right, and we have the butterfly now rendered. The only thing we would be able to do is composite them in screen space, which means that they would not easily, trivially take into account depth, or we have to go again and like use other compositing features and try to finagle it into the pipeline. What we can do instead is we can have another look at this where we have, again, all these objects lined out, but we can first choose to aggregate them into a common space and into a common splat structure. So this means transforming them into one coordinate frame before sorting, so that sorting can then happen unified. And so in that case, all these like depth compositing problem automatically happens, and then we can render them. This has multiple advantages because we can very easily now sort them a second time if we need a second viewport, and can render them there with limited cost because the aggregation step has already happened, and that simplifies the whole thing. Even more, if you think about this aggregation step, it's already applying local coordinate transformations to all the different splats that we have. And so we can generalize this transformation a little more, right? So we can, for example, apply additional rotations for select splats, or we can apply additional shifts for select splats, or even apply any kinds of transformation on the spherical harmonics or any other representation that we have for the material or the appearance parameters that we have. So that creates a very, very flexible and powerful system that can run at high efficiency. Let's have a look specifically at how this can help us do dynamics and animation. There is two major cases that need to be distinguished here. Classic dynamics mean mainly that we have one set of splats per frame, and they usually are created through recordings, a reconstruction of that dynamic recording, and then a fixed replay. So they're not as easy to animate or edit because we don't know correspondences across frame, and we just have to basically sequence them out and replay them one by one. And I listed one of the earlier papers that attempted to do this right here. In contrast, if we look at animated 3D Gaussian splats, in that case, we have a skinned rig of splats and one set of rig transformations per frame, but only this one rig and only this one set of splats, right? So this is fundamentally quite different. It allows us to change these transformations per frame and to animate them in a dynamically controlled way that can also like depend on input or on preference, and it is easier to edit them. There's also a line of work that looks at specifically this type of animation. I listed again one example of that here. Now the question is, if we have such skinned and rigged splats, how can we animate them? we looked back at the literature that does that, and one of the criteria that is particularly important to animate splats is that the transformations are volume preserving. Because the splats occupy a specific volume and they composite in a volume, it is critically important that we achieve that. Also, that has been done already quite well and covered in literature, and we chose in this case to use skinning using dual quaternions. I listed the reference at the bottom of the slide that fulfills that. In a nutshell, we are still looking for a transformation for each vertex position from its original space to a transformed animated space. In this case, we can create that as easily as using the specific, creating a weighted sum of the dual quaternions that describe those transformations to create a single dual quaternion that represents it. That then gets split up in the real and dual part. And from that, we can very trivially create one single transformation matrix that can then just be multiplied to the with the vertices. And that's it. That works actually very, very well. And I'll hand it over to Andreas to show us and walk us through his demo.
Hey, everybody. So we are going to attempt to show you this kind of running live in some demos. So if you go to forge.dev, which will be renamed shortly, you can see all the code examples that show some of these things. This is actually a collection of other examples that we've been developing in-house. And I'm going to show you a couple of these now. So let's first take a look at the butterfly. You can see this is a very kind of shiny, bendy butterfly. And the way it was created was essentially asking ChatGPT, make me a beautiful metallic butterfly, and then dropping that into the Microsoft Trellis open source project, which can output both meshes, but also Gaussian splats. So if I kind of move forward here into the butterfly, you'll start to see that it's actually made of lots of Gaussian splats. And they're all kind of animating, moving around. So just as Christoph mentioned, if I click on, oops, there's a little bit of lag and latency. Now, I'm not sure, hopefully you guys are seeing this as relatively smooth. If it's not, I'm gonna blame video encoding. But if I turn on the skeleton here, you can see we actually have the literal bones that are used to animate this butterfly. And let me turn off the butterfly. And this is created programmatically. It's essentially a 15 by 15 regular grid of bones. And each one of them is being animated with just a simple sinusoid that we came up, kind of shader toy style. And every single splat within the butterfly now has the 4 bones that are closest to it. And they have bilinear weights so that you can see that not only do the bones kind of move, but everything kind of in between the bones also very smoothly animate. So exactly what you'd be able to do with meshes, we can now also do with splats. So let's see, let me go back now. Let's look at the next demo. So next I'm going to go into the playground here, which has a whole bunch of interesting things. You can see the butterfly again. Everything you see around you here, by the way, is made of splats. So this the world, the scene, we have this butterfly here. If I kind of get a little closer, you can see that this butterfly and this other grid of axes, they're kind of sorted and blended together perfectly, right? Like every single frame, you can see that they're, what's supposed to be in front or behind the other one is happening in real time. But I also kind of want to show you what we can do beyond that. So in Photoshop, you have this concept of layers where you can essentially apply like color edits, right? And they're applied one after another as a sequence. So as part of Forge, we have a programmable pipeline. And one thing we built was a sign distance field evaluator that can be used to recolor the splats and also displace them. So I've added a layer here, like you would add a layer in Photoshop. And now let me add a sign distance field to it. So that you can see there's different shapes, right? And we'll just stick with sphere. And I can kind of take this and move it around in real time. So, oops. As I'm moving it around, you can see that all the Gaussian splats are kind of like being recolored in real time. And I can also, oops, let me bring this smoothing down so you can kind of see the edge there a little better. I can also invert it. right? As you would expect to do the sign distance field. We can add multiple sign distance fields. So let me make a blue one here to kind of distinguish it a little bit. And oops, this guy around. So, whoops. So one thing you can do here is you can actually do this real quick. Oops. It's down a little bit. It's tricky with latency. So one thing I want to show you is that, sign distance fields, you can actually do smoothing across them. So you see, like, as I pull this slider, it's computing a sign distance field value that's an exponential weighted average of the colors. I can also smooth across the inside-outside boundary of these splats. And what's that? Oh, yeah. And finally, I can also bake these edits into it. So now you see that the sign distance fields are gone, but the colors have actually kind of changed. Let me add one more thing just to kind of show you something that you maybe haven't seen before, but we can also use this sign distance field, not just for RGBA, but also for XYZ displacement. So let me make a green one here just to kind of really quickly show you what I'm talking about. So I'll move this here. And so not only can we edit the colors in real time, but we can actually also displace them. So, oops. So now, we want to kind of give the opportunity for people to play around with these things. What can I build if I can real-time deform these splats around, right? So let's do that. Because I'm running out of time, I'm going to quickly kind of switch.
I hate to cut off this great presentation.
We're out? Okay.
About 5 minutes for questions. So
okay. Yeah, let me just show you so we can also kind of have multiple cameras. This is the last thing. I'll just add a couple of cameras here, but just to kind of show the point of being able to store multiple things at once. You can see everything's kind of happening in real time. So I'll stop there.
Thanks a lot. And let me, I'll take the mouse back here and we want, I'll jump right back in here and put the takeaways on screen real quick. Because this is very important for your mission that you mentioned at the beginning. Just calling out real quick, I think especially splats can be animated using well-known techniques. Vertex transformations translate very well to splat transformations. There is no consensus yet at all around storage and implementation. From our opinion and point of view, I think there is some consensus around storage of splat properties, right? For example, POA covered that really well in all the formats that we have seen so far. Also there, it would be great if that were better and more fully consistently defined, for example, color space orientations, etc. We'll leave it there. Diego Marcos is joining us here also for the Q&A. He's the creator of A-Frame, who has also been working with us on this and supporting us. And yeah, let's dive right into the Q&A. Thank you.
Thank you. And we don't have the actual questions, surprisingly. So it's a reminder, you can use Zoom either or Discord link. But I have my own personal software engineer hat on me today, and I have a question for you. So 2 of them, again, I don't want to occupy all the time. But first one, why do you choose the dual quaternary? And second one, what about authoring of the assets for this animation-friendly format?
Oh, yeah, maybe I can start with the first question. So Forge is actually a completely programmable rendering engine. So we chose to implement dual quaternion because it has volume preserving properties. And if you imagine reconstructing a real person, right? Generally speaking, you're not having cartoon-like deformations, and it does generally lead to kind of less singular and weird cases during animation. But we could also do linear blend skinning in Forge. There's nothing that stops that, but this seems to be kind of the direction that some research is taking. So I think that's why we chose that as an initial starting point. And I didn't quite get your second question.
So now I need to remember it. So what about the authoring for this? Because dual quaternions, it's not trivial.
Yeah, no, exactly. This is kind of a new area. So you can actually take the same skeleton you would use for a mesh and literally apply that in Forge and animate a system the same way. So you have to be able to produce, a mesh and splats at the same time. So we can do that with Trellis. I'm not sure if the tooling yet exists to kind of do these same things for Gaussian splats, but really it is very analogous to animating vertices in a mesh. So I believe it will get there. And we hope that this renderer gives people an opportunity to explore that direction.
To add 5 cents to the first question that you had about like why specifically the quaternions and why the volume preserving transformation, everything that Andreas said, yes, absolutely. Plus, I think it's very important to keep in mind that the blending of Gaussians does rely on where they are located and how they composite in the volume, right? So I think it is much easier to destroy the appearance that you actually aim for and that you reconstructed or that you created with the Gaussians if you destroy the volume structure that they are located in. So by trying to avoid that, I think it also really helps us that they still look good. So it does have an additional implication on top of like what we classically would see with the disadvantages of like volume preservation in some cases of meshes, specifically in the case of Gaussians.
Thanks. Really appreciate your answers. So we have questions incoming. But we're running out of time, so we need to move over for the next presentation. We are hosting the Q&A session at the end of this town hall. So I will ask the questions as a follow-ups. Just prepared. Thank you very much. That was amazing demo and amazing presentation. Thank you. And we are moving for the next presentation. Zian, this is your turn.
Okay, so thank you for having me here. So my name is Zian. So I'm a research scientist at Nvidia. So I think today's talk, I wanted to share some research trends we are seeing from the community towards building graphics compatible 3D Gaussian assets. And hopefully we are going to discuss how they may impact the standardization of 3D Gaussian splats. So before we dive into the 3D Gaussians, I wanted to take a moment to appreciate what traditional computer graphics has already achieved. So what you're seeing here are examples of classic post-trace rendering. So these are mesh-based scenes and not 3D Gaussian splats. You can see very complex effects like accurate reflections, refractions, and soft shadows, global illumination, and they're handled with precise material and light modeling. And classic graphics platforms are still incredibly powerful, and they are the most mature tools we have for content creation. And that's like decades of wisdom for the graphics community. And the challenge of traditional pipeline is they're just costly to use. So creating high quality content still requires significant time and manual effort. And that's where the 3D Gaussian splats and neural reconstruction method in general start to change the landscape. So instead, we don't need to author the scene from scratch. We can now capture real environment and turn them into 3D assets and make it much faster and easier to create immersive content. And lower the barrier for 3D and make it accessible to more applications. And this makes us live in an exciting time. So 3D technology is promising to transform in many aspects. And in reality, you often want to mix these like synthetic virtual objects with real capture scenes. And that may mean these neural representations and traditional graphic systems now need to work together. And that have new important questions arise. So like, how do we store the scenes and how should they be rendered? And how do we support them in real world systems? So in this talk, I'm going to cover 3 research directions that's important for real world use. So they are material reconstruction and physically based rendering and lighting related to 3D Gaussians. And these are still active research areas. And you will see research publications from many different institutes. And a lot of these techniques are still early stage. So there may not be a product to use yet, but they are moving very fast. And they might influence how like 3D Gaussian splats evolve. Let's start with the first part about materials. So the first thing is why materials matter. We can start with a practical example. So imagine you're capturing 3D assets using Gaussian splatting, maybe something like this. It could be a product for e-commerce. And now I just want to change the appearance. For example, like I wanted to fit this background better to make it look more natural, consistent. And with 3D Gaussian splats, by default, this is pretty difficult because the color or appearance is now baked into the spots. And to relight this scene, so we need to understand not only just its shape and color, but also how surface interact with light. That is material properties, the things like base color, roughness, and reflectivity. And in classic graphics, so these are usually carefully designed by artists manually. And in real-world reconstruction, we have to estimate them directly from the data, the input data. And this task is actually not a new task. It's recovering these physical properties from images. It's also known as inverse rendering. Also for graphics workflow, it's also known as delighting. And it's not a new problem. The original formulation already dates back to like several decades ago. And back then, researchers already realized it's a pretty challenging and important problem to estimate reflectance, geometry, and light from the input images. And in the context of 3D scene capture, so the input is typically a set of post images, multiple views of a scene with known camera parameters. And the output of the neural representation should capture not only just geometry, but also like base color. That's like how the intrinsic color of the scene look like, and also material properties. And as a comparison, standard 3D Gaussian pipeline usually only focus on geometry and color. And most of the inverse rendering are actually using a pretty similar optimization framework. So given the input images with known camera poses, the scene is still represented as 3D Gaussians, but they are going to have extra attributes. And there will be like differentiable renderers to render them into images. And the supervision is again still very similar. They're going to come from reconstruction laws to minimize the difference between the rendered views and the input images. And additionally, they will require more regularization terms like neural priors about these material properties and geometry properties. So let's dive a bit deeper into this, what this means for scene representation. So a typical 3D Gaussian scenes will store RGB color per Gaussian. So usually they're represented as spherical harmonics parameters because you're also going to use this to capture view-dependent effects. But for these material-aware splats, so each Gaussian will require extra information. For example, like you may have base color and metallic and roughness, and maybe ambient occlusion. So like that's like 3 + 1 + 1 + 1. So that's like 5-6 channel extra channels. And in addition, during rendering, surface normal properties are often very important. And computing normals from Gaussian splats is usually not very straightforward. So they can also be stored directly per point. And with this modification to the Gaussians, you can now still similarly, just very similar to how you render the Gaussians, render the Gaussians with color. You can now render them with different properties like the materials, like albedo, roughness, metallic, and surface normals. Okay, so then we can know what this means for file formats. Actually, it's pretty lucky. So most research projects usually follow the standard physically based models, like the Disney BRDF. So in principle, we know what are the parameters one is stored. So it's usually just extra attributes. So this design is not very challenging. So it's fairly deterministic. So the research trends or the harder part is more on the reconstruction side. So how can we reliably recover the material properties from real world data? And in the meanwhile, there are also growing interests in neural materials. For example, now we don't need this base color and metallic roughness, so we are like standard descriptions. How can we use neural networks to approximate how light reflects? So yeah, this is like still an open area. So maybe it's also something you want to keep in mind when designing for future flexibility. Okay, so now we can kind of have the material properties. And the next challenge is how we actually is going to render them. So this turns out to be one of the most open-ended problem, and they're still not like a universally agreed pipeline. So let's take a step back and look at classic rendering, because classic rendering also first starts with rasterization-based rendering. That's pretty fast and simple. And later they evolve into ray tracing and path tracing for higher quality lighting effects. So here is a result. So this one is actually looks pretty good. This one is rasterization-based results. So basically with this material, extra material channels, this is also what we already can achieve with the 3D Gaussians. And now I wanted to switch to ray tracing. So on top of this, so a better rendering algorithm, like ray tracing, path tracing, they can be used for rendering complex effects like reflections, refractions, or more accurate shadow when this needed. So again, so this is rasterization. You can see it a little bit like this old-fashioned game style. It's generally like not bad, but we can do better when we have a better rendering formulation. And the question is, how can we do that with 3D Gaussian splats? So one straightforward idea is like, maybe you already heard like there are works extending like not just rasterization, but also ray tracing to 3D Gaussian directly. In fact, yes, there are already papers showing how to ray trace Gaussian splats. In theory, we could just apply this recursively to simulate full path tracing, scattered arrays. But the problem is performance. So the first ray, the primary hit, is usually pretty fast. But as it hits the surface, the ray will scatter and bounce. So the number of rays is going to grow exponentially. So without fast acceleration structures, so Gaussian splats can be very, very slow to render. So to make this more efficient, one of the common strategy is to pre-compute and bake the visibility for scatter rays. So that's also some of the like very standard approaches in graphics. So instead of tracing at like multiple bounces at runtime, so these methods is going to pre-bake the occlusion to indicate whether light is visible. For example, like at this location, I want to know how this surroundings look like. So there's going to be a 3D Gaussian. So this method will first render a surrounding, like kind of like a panorama or cube map around to understand what is the geometry there, and the occlusion. So it's like a binary mask, and it can be convolved and computed as spectral harmonics coefficients. And these coefficients will be extra channels to be appended on this Gaussian. So this is like one approach to allow us to approximate soft shadows or indirect lightings without the full cost of path tracing. And here are some examples. So how these methods can achieve. So this, by the way, this is from a work called GSIR. Yeah. And another workaround that, because people are usually very excited about 3D Gaussian splat, and another workaround that sometimes we may forget is to bring meshes into the loop. So meshes are so well optimized for ray tracing. So one really naive idea is like, if you can just convert Gaussian splats into mesh approximations. So actually sometimes it can work. So especially if the surfaces are very simple, but the downside is also very obvious. It's going to lose quality, like a very thin detailed structures is going to lose. So that also leads to the idea of hybrid representation very naturally. So for example, we can keep the Gaussians for primary rays. So basically the first hit, because that's where you get the most quality and high frequency details. And we can just put in the mesh proxy. We can rely on meshes for secondary, like these scattered rays. So this could give us the best of both worlds. so we can have fast shading and better support for complex effects. So let me show you a visualization how this could work. So first, we may find ways to convert the 3D Gaussians to explicit meshes, for example, shown here. And during rendering time, we will first find the hit location of the camera ray, and we can scatter the rays to the sky dome, the environment map to render shadows. So basically the first ray of the G buffers, we can still use Gaussian rasterizations to generate these G buffers, but we just use these underlying proxy meshes to render shadows. So that could be a way to go from here. And so as you can see, so even once we already have these reconstructed materials, there's still no agreement yet on how rendering could be done. So the choice is between rasterization and ray tracing and visibility baking or hybrid method. So it's still pretty much under development. So that is make it pretty important for formats to stay flexible about these acceleration structures. And the last topic I wanted to quickly touch is about lighting. So in earlier parts of the talk, we treat 3D Gaussians mostly as assets, things like objects that can be inserted into new environments. But what if we want to do the opposite? So now we can bring, we can first reconstruct capture 3D Gaussian environments. And now we want to bring synthetic assets into 3D Gaussian scenes. So this is especially important for AR or compositing. So in this case, the 3D Gaussian itself, the difference of in this case is the 3D Gaussian itself will need to act as light source. So there will be emitters. So for example, here, now, if you want to insert something like a mirror, specular sphere, or transparent sphere, or like here, it is like inserting some virtual contents. And there are also standards for emitters or lighting in graphics. So to better support this, we may need not only just these LDR colors characterized by stereo harmonics. Potentially, we also need to expand the dynamic range. For example, in outdoor scenes, so the sun may be sometimes very bright. So it's like much brighter than the regular images could capture. So that is like a potential consideration we need to consider. And also, if the 3D Gaussians is going to expand to HDR colors, so there will be also other, just like LDR images and HDR imaging. So Gaussians can potentially also have HDR Gaussians. There are extra parameters like exposure values and tone mapping parameters. So they could also be packed together into one file. Okay. So it's close to using all the time. So to wrap up, quickly summarize. So I'm trying to talk about 3 active research areas. So the first is material reconstruction. So the file format design is pretty deterministic. So it's probably just extending the color channels with additional Astro standard material properties. And I think the research is more in motion to get better quality that is passing the productization threshold. And it's more in debate about how we could render them with physically based rendering methods. So the key research consideration is still on what is the best acceleration structure for it to make it very efficient in runtime, but also generate very decent results. And another aspect is Gaussians can also serve as emitters for lighting. So this part is also kind of deterministic in file formats. An easy way to do we can expand the LDR color to HDR and additional parameters for tone mapping exposure. But they're also similar to material reconstruction. The research trend is seeking to accurately reconstruct high quality HDR contents. Yeah, so that's all I have today, and I'm happy to take any questions.
Thank you very much. So we don't have questions yet. So again, I have to put my software engineer hat. When you expressing the acceleration structures, can you maybe a little bit go deeper? What do you mean by this case? Is it
Yeah,
for ray
so
tracing or for the specifics, for the splats, etc.?
yeah, I think the general takeaway is like the best acceleration structure is still under development. One of the ways like we are discussing about is occlusion baking, right? So we wanted to understand for each hidden location, so how whether the light is visible at that location. So this could be just baking extra spherical harmonics parameters onto each Gaussians. So this way is like kind of like an easy approach. So that is one way. I think that it's also like something like that's quite widely adopted in classic graphics. But the downside is like the quality still have room for improvements. So we still cannot handle the global illumination and these very complex effects. Yes, so that's this part.
I see, but like it still would be only a self-occlusion, right? In this case, because you cannot consume the other assets around.
Yeah, that is self-occlusion. Yeah, that's true.
So, and I have
Got a couple of questions too,
yes,
Alexey.
I see the first question comes in, so I will just read right away. So, what is your advice to SDOs to build better standards that realize the rapid pace of innovation in 3D assets rendering techniques? For example, convergence of AI and 3D Gaussian splats.
I didn't see the.
It's very bottom of the Q&A session.
Yeah, could you remind like what is the emphasis of this?
And so basically the emphasis
Oh
is
yeah,
how to build these distance fields.
Yeah, I'm trying to share like, so what are the landscape that's already like pretty deterministic and what are the things that's still in motion? So from my current view is like for the file formatting side, so how we describe materials and how we describe lighting, like HDR lighting is pretty much deterministic. So we can just be pretty prepared, like, so there are new assets that is reliable and graphics compatible. So they're going to follow the graphic standard. They're going to have the material properties like base color, metallic roughness, following the BIS DPRDF. So this part is pretty much deterministic. It may take the research community some time to get the quality ramp up. I think recently they have made significant progress to improve the downstream D-lighting task quality. And I feel very hopeful, like maybe sometimes in the next 6 months, 1 year, so there'll be like very impressive 3D like assets with high quality materials. So that's one direction. And on the other side, like I think like the thing that's most under debate and emotion is how we render these Gaussian splats. So this is like something like pretty tricky. So it may have like several different renderers. So they're like research prototypes. So I think this part is something like requires more attention. For example, like how can we ray trace secondary rays for Gaussians? And maybe how can we blend 3D Gaussians into real environment or synthetic environments and properly cast shadows and reflections? So these still requires further discussion. Yeah.
Thanks. It's another question, just statement that the way how you represent PBR materials, it's super important and makes basically pipeline friendly for the traditional rendering that we have today. Return back to kind of your the sentence you said before. Do you think like a G-buffer approach you presented already, that can be the way we can go to combine the Gaussian splats rendering plus the traditional forward rendering or whatever, like deferred rendering? So what do you think? Is it way to go that we can standardize this at some point? And that might answer some questions because you can use ray tracing, path tracing, whatever, to maybe to do some additional.
Yeah, I think like if we can get this, it is in the most foreseeable like ways we put like because materials yeah, so the most standard materials are also like I think like yeah, even for now, like people don't there are many like material definitions. So the most commonly adopted, like maybe in Unreal Engine, so there will be like this simplified Disney BRDF. So that's like a pretty widely adopted standard. But there are like also custom material shaders and mixed shaders. So I think maybe a similar position for 3D Gaussian slots. So we can have like just follow the previous standard, and we are having one like widely adopted, and maybe like for in-house application there will be like other adjustments on top.
Okay, great. Thank you very much. So we are perfectly in time, and please again ask questions into Q&A Zoom section. Zoom section. That will simplify the life for all of us. And for presenters, please answer the questions like in this spot as well. Again, they'll just not sure if we have enough time to answer all the questions. Thanks, Zian. And we are switching over for the next presentation, which is Wieland. And yes, please go ahead.
Yeah, thanks for organizing this event. I will talk to you a bit about 3D.js compression. I'm a researcher at a Fraunhofer Institute in Berlin, in Germany. If you don't know Fraunhofer, we are doing applied research over there. So what I'm showing on this slide is a bit of compression. That are the images in the middle of the slide. That's actually a compressed 3D.js scene. And then on the right on the side, the right of the slide, there's a bit about this format that we've been working on to describe the different compression formats that are already out there. I've been coming into this field by looking at 3D.js when it came out and was interested in it's a large 3D scene that is very sparse. Can you actually map that into a two-dimensional space? And it turns out you can. That's a bit of the animation we see going on here of this 3D.js thing being mapped into a 2D grid. And it turns out this is really useful for compression. If you map your Gaussians into this 2D grid, then you can then save your images with a normal like JPEG or PNG or WebP, whatever image. And this is really great for compression. So this scene that was originally like 640 megabytes for this truck now goes down to 30 megabytes and a bunch of images that are really easy to decode. And then you give the same data to the renderer. The renderer doesn't need to change at all, which is pretty fun to implement a decoder for it. And so people did that. For example, Vincent Wu, who built this lovely demo at the beginning of the year of this Sutro Tower, this TV tower in San Francisco that he captured, showing the scene in only 30 megabytes running in a browser with the Play Canvas engine. Go check out the demo if you haven't seen it. It's a great experience and showing how if you compress your splatting scene down really far, it makes for a great experience in, for example, the browser. Something I built a week ago was for a paper of a colleague, Florian Bartel, who was working on generative head models. So you would have a network that's like a gigabyte in size that can create these heads of people, these synthesized heads. And now it's hard to stream the network to your browser if it's a gigabyte in size. But what we can do is we can stream these created Gaussian scenes by compressing them with a self-organizing Gaussians method to only 2.7 megabytes per identity, which is like the size of a large image, but these are actually 3D Gaussian splitting scenes. And this again is using the Play Canvas engine and the self-organizing Gaussians compression. While we were working on the compression, we noticed there's a lot of academic papers coming out, and some of them compare against other papers, some compare on some data sets, some on others. And so to get a better overview over this field, we started this 3ds.zip website where you can explore many of the academic methods that are out there to compress your Gaussian splatting scenes. This became a Eurographics paper that we presented a couple of weeks ago in London. But still, now that we have a framework to compare these methods on the same data sets with the same, same test images and same resolutions and so far, and so on, there's still many ways to interpret the data. Do you look at the PSNR, so the color of the pixel differences of the rendered things, or do you look more at a perceptual metric? Do you perhaps look at the number of Gaussians? So do you want to compress your scene by reducing the number of Gaussians? There's many different ways to look at this kind of data. And so taking a quick detour, something that's very, I think, important when you're looking at 3D.js compression is it's different from traditional image compression. So in traditional image compression, you would have your input image. You would go through this encoder, do some kind of encoding stuff through a decoder, and you get a decoded image, and then you can compare the quality of that. If we move on to Gaussian splatting, what we have is this kind of point cloud. 3 Gaussian splats is no more than a point cloud with a couple of additional attributes. And then we can encode that, decode that, get out another point cloud. But what we're actually interested in is the synthesized images, right? The rendered images. And so this point cloud that we have and that we are feeding into the compression is actually something that was trained from 2D images as well. And we are comparing this, the images against other images. And so there's the compression part that people mostly focus on, but there's also this part, like how did we end up with this exact point cloud? And I would urge you to consider these two problems together, because it's really important and a really great opportunity also for this 3D.js compression, that you can actually change this kind of point cloud and make it nicer to be compressible, have there fewer Gaussians, have smoother Gaussians, and so on. When we looked at all the methods, I cannot go into detail about this. If you're interested, please look at the Eurographics paper. There's a lot of steps you can do to compact and compress your Gaussians, like have different parameterization, maybe instead of the spherical harmonics, use some material properties, densify your Gaussians, use anchors, or use more efficient rendering where you will need fewer Gaussians. These are some of the tools available. For compression, there's even more tools available, like non-linearly mapping your values, using codebooks where you have to store smaller codebooks and then just indices into these codebooks. Structuring, like self-organizing Gaussians. Normal scalar quantization. Again, regularization, making your surfaces smoother is great for compression. And then traditional coding, or using image compression like in self-organizing Gaussians, so you don't have to do the coding part at all. And so what we wanted to do is to somewhat build a format describing these different tool sets and toolboxes that you have. Because there's a lot of methods out there picking and choosing some of them and combining them. And it's really hard to tell, so what's the best compression format for 3D.js out there? Because some using some subset of these methods and others are using others. We set out to build this kind of self-documenting format that describes how actually one 3D.js compression looks, hopefully making this then interoperable and then being able to develop future formats that are better than what's currently out there. And so we're starting by describing how the INRIA PLY point cloud format looks, how maybe the self-organizing Gaussians format look, and we'll also do something for SPZ, which we will hear about in the next talk, I think. So in this tool, you would usually get in some kind of PLY format. Then you would have the description how to actually decode that, get out your scene, then have some parameters to encode this in another format, for example, self-organizing Gaussians. Be described how this looks different now that you're decoding that. And then you'll get another scene in your memory that is a slightly different representation. You can render that, look at the different images, how they differ, and evaluate what the compression did or didn't do for you. And so it starts off very simple that this, for example, PLY point cloud format that was used in the original 3D Gaussian splatting paper has some mean parts that you need to know about. For example, the scales are in a logarithmic scale, and the opacities are remapped with a sigmoid function, and your spherical harmonics need to be actually permuted. So dimensions need to be changed. Otherwise, if you look at your spherical harmonics, which has happened to several people I know, your view-dependent colors get all wrong. And this is not really described in the paper. It's kind of implicit knowledge by reading the code base of the original 3D.js paper, and we want to make that explicit so it's easier to reason about what these formats are. And so, yeah, our code is currently ongoing, trying to get that running. I just made the repository public a few minutes ago, so you can have a look at it if you're inclined to look at kind of researchy code. It requires a computer with a CUDA capable graphics card currently to run that, which probably somebody in your organization will have, as you kind of need to create the Gaussian splats in the first time. Yeah, let's look at a demo how that works. So we will have a kind of web viewer that's maybe if you're familiar with something like Nerve Studio, you know that already. You can explore your 3D scene, which again is here the track, and we can run this evaluation, which will use the test set of images that you maybe kept for evaluating how your scene looks. And so it runs these against the rendering, and in this particular version, we've already used mini-splatting to reduce the number of Gaussians, and so we ended up with a PSNR of 25 and a size of 80 megabytes, which is already like factor 8 smaller than the original INRIA version. And then we run our 3D.js SOG. Let me quickly stop the video. We run the SOG conversion here, and you can see running through some of the encoding of the PLAS, the parallel sorting, which does this smooshing into the 2D grid. And we end up with a compressed scene, which we can then switch between and look at the results. And then we can run another evaluation of our now compressed scene, and hopefully it'll still have a high quality. In this case, we dropped the PSNR by 0.02, but the size was now reduced to 5.4 megabytes. And if you remember from an earlier slide, the original truck scene in the INRIA 3D.js was 640 megabytes. So with the reduction in number of Gaussians and then applying the self-organizing compression here, we get over 100x in reduction of the compression. And then the goal with this tool is to find the best compression for your scene, because depending on whether you have a small scene or a large scene, the parameters you would need to compress might be quite different. So in this case, I'm just showing that if you're only using 1 bit for the opacity, your scene obviously breaks. But I hope you get the idea that you would change out different parameters of your compression scheme and then find something that looks really well for what you're trying to do, but gets the smallest possible size. I wanted to give a quick shout out to the Mr. Nerf Discord. Hopefully you've already all joined the Discord for the Metaverse Standards Forum. So if you're on Discord anyhow, hop on over there as well. If you're interested in radiance field research particularly, so that's what it's about. Maybe you're following Mr. Nerf for the updates on what's going on in the radiance fields community. And it's really great. Little community. I've posted a couple of screenshots that I looked up, random screenshots here, but you have people talking about current papers, you have people talking about code, you have artists creating scenes, you have people looking at formats, and all kinds of interesting stuff. So yeah, my call to action would be, remember from earlier in the talk, compression always goes together with compaction. We can actually change and should change how the scene looks, how our Gaussians are placed, because that helps a lot in compression. Yeah, Fraunhofer again is applied research, so please tell us about your 3D GS compression needs in industry. I personally also would be very interested to hear, to not work in a vacuum. And if you want to try out this like pre-alpha demo of the FF Splat tool, then come around to the repository. And otherwise, you will find all the like links for the self-organizing Gaussians, for the compression survey and so on under 3dgs.zip. Some questions I had during the Eurographics part that I found interesting, which are kind of unsolved, was how do we, like, people are talking about compression and they have a scene and they compress that and send it off. But yeah, involving artists, how do you then resave that, right? You did some editing, some authoring. How do you re-edit your scene? How do you recompress that without losing any of the quality? Can you apply the same algorithm several times? So I think an interesting question that's not really answered yet. Also, I would be interested, how do we handle like level of detail? How do we handle really, really large scenes? Yeah, which I find an exciting topic to work on. And so I'll leave you with this lovely demo. Please go check it out if you haven't already. It's recorded in an Austrian church by Schindler 3D with Photomento and hosted in the Play Canvas engine. So just type in, I don't know, Play Canvas church demo or something in Google and you will find it. And this is using the self-organizing Gaussian compression to compress the scene from like 1 gigabyte to 55 megabytes. Yeah, running in a browser, and I think it's really beautiful. So I just like showing it off. But that concludes my talk, and I will have a look at the questions, or maybe Alexey can hand some to me.
Thank you very much. Thanks for the presentation. Again, please put your questions, preferably into Q&A session of Zoom. So we have no questions yet. I'll start with my questions as usual. First one, if we can kind of combine with the previous Zian's presentation, do you think it we should support multiple techniques for compression for the PBR materials, like additional properties, etc.? What do you think on this one? So let's assume we have unknown amount of properties that we need to keep. How you want to design this compression pipeline?
So yeah, that's also maybe one motivation why we are trying to describe the pipeline as, in this case, a set of a YAML file that describes what actually is going on. So this is again the sample for writing an INRIA PLY file, but it will be similar for like SOG or SPZ or these other formats. And you would go ahead and describe, okay, I have these, for example, spherical harmonics, and what I want to do is I want to split them into two parts, which is the AC part and the DC part. Maybe if you're familiar with like PLY reading, you know this. And then I want to do other steps that perform a set of steps. And setting this up now, which actually took us quite a bit of time to get this right. It looks quite simple on the surface, but it actually was quite an involved process of getting there to make this work for PLY and self-organizing Gaussians and other formats. And once you have something like this, you can combine these different operations and add like new parameters. So currently this scene, we're saying, okay, we have means and scales and opacities. But then it wouldn't be that hard to like add, okay, we want actually not to use spherical harmonics here, we want to use some BRDF material, and we would encode this by maybe putting this in another image on top of that and giving all the Gaussians material attributes. So I'm very interested into experimenting with something like that. And so this format that we're working on is actually very extensible to do actually these kinds of things. Maybe you want to use 2D Gaussian splats and not 3D Gaussian splats. Maybe you want to use a different kind of primitive, not the INRIA primitive, but a different splat that is rendered differently and stuff like that.
Great, thank you. So we have a couple of questions. First one, have you also tried to store 4D Gaussians as a video? And so the follow-up questions, what do you plan to use glTF as metadata storage for compressed buffers, or you prefer some other metadata storage?
So the first question is, yes, we're working on that, and I think it's a very exciting direction to do that, the 4D Gaussian splats, and yeah, I think it's a good extension of what we're doing here. And so if you're interested in that, please get in contact. So the repo is currently for static scenes, but yeah, that's definitely 40GS something that's of interest to me as well. And about the glTF stuff, so I know that I think we'll hear more about that in the next talk. So I'll be interested to get an update on that as well. For me, the best format for storing 3D.js itself hasn't been found yet. And I think it's not yet time to settle on that. We should still experiment and implement different things. And then, yeah, I think something like glTF would be a great thing to host the metadata and host the buffers of that.
Okay, great, thanks. So the next question, once decoded, is the splat back to a full size in memory, or it can be images produced by self-organizing Gaussians and like sort of GPU compressed or like a decoded, close to decoded KTX-like formats as well?
So in most implementations, people will decode everything back into GPU memory, but I think this is an implementation problem. First part of the answer, you also have code books, so you don't need to like look up all the codebook values to represent that. For example, you have a codebook for the spherical harmonics, also in the self-organizing Gaussians, that is much smaller than the actual data if you uncompress the law. That's fairly easy to do and straightforward on the GPU. And for using like texture compression on the GPU, I think that's possible. And I think RSP also experimented with that some time ago. It's definitely some exciting thing to try out. I haven't personally done it, but I think it's definitely possible to also save space on the GPU that way.
Great, thanks. The next question is, so it's about the issue of temporal flickering in dynamic Gaussian splatting. In your view, should efforts to mitigate this flickering focus more on the representation side, such as ensuring temporal consistency and stability in the splats themselves, or on the compression side by developing codecs that will be more aware of temporal artifacts and better at preserving visual coherence across frames? Or do you believe in a hybrid approach is necessary?
Yeah, that goes a bit like, back to what I said in the beginning, and I'm, a fan of considering these things hybridly because I have seen how much, better the coding gets if you consider the whole pipeline. And since 3D Gaussian splatting or 4D Gaussian splitting as well is, has a differentiable renderer, and we have all this great code that can propagate all this data from your rendered image back through the renderer and maybe also through the encoder and decoder and back here. It's great to combine this whole pipeline and look at an optimization of this problem as a whole and not of the parts independently. And this goes for compression and compaction for static scenes, but this I think should also go for temporal stability and compression of temporal data for 3D Gaussian splits.
Great, thanks. And so next question, any insights you can share about compressing Gaussian means? Have you found any success on addressing that?
The means, so the positions of the Gaussians themselves are the data that requires the most let's say bit depth or the most detail in the format. What we're using in self-organizing Gaussians to try and reduce that a bit is a nonlinear mapping like this one that like gives more detail to the center of the scene and gives less detail, like higher quantization steps, let's say, to whatever is further away, like sky stuff. If that's a bit in the wrong position, your sky Gaussian, that won't matter that much. But obviously this only works for scenes where you have the most interesting part in the center of your scene. But yeah, this is one of the things I think that can be explored further. How do you properly map that non-linearly? And yeah, you can see, for example, in this structuring part here, so one of the self-organizing stuff, if your splats are organized smoothly, or maybe let's look also on this thingy, something like this is much easier to compress, right, than something like this. So if you consider that you want to compress your data, building smooth surfaces where the Gaussians are somewhat spaced apart in a more little regular grid, that helps compression by a lot. So again, if you consider that like hybrid model, or consider that together.
Okay, thank you very much. We are perfectly in time, so thanks for this great presentation and thanks for the questions. So you definitely makes my life easier. And
Thank you.
We have the next presenter. Projit, it's your turn.
Well, hi everyone. I'm Projit Bandyopadhyay, a senior software engineer at Niantic Spatial. A bit about me: I've worked across a wide range of domains, from like web security and natural language processing to distributed systems with Kubernetes for 5G telecoms, and for the last couple of years, AR infrastructure and 3D reconstruction to enable immersive augmented reality experiences. I'm also one of the maintainers of our open source file format, SPZ. At Niantic Spatial, which was actually just formed last week, spinning out of the acquisition of Niantic by Scopely, we're on a mission to build a geospatial AI model that we believe will transform how we live and work, powering the next era of spatial computing. And as you can probably imagine, Gaussian splatting is a big part of that story. And central to making that work at scale is our infrastructure for storing, rendering, and sharing splats, specifically our custom file format SPZ. So I'm here today along with Jason Sobotka from Cesium Bentley to dive into SPZ and talk about some of the progress we've made in integrating SPZ into glTF. So what are Gaussian splats? A small refresher on Gaussian splat components in case anyone at this Gaussian splats town hall may have missed what they are. Gaussian splats are oriented 3D Gaussians, or ellipsoids, placed in space. Each one carries not just a position, but also orientation, scale, color, opacity, and sometimes shading data for nice specular effects in the form of spherical harmonics. When rendered to the screen, these splats blend together smoothly to create dense, photorealistic representations of a scene without needing any meshes or explicit surfaces. This makes them especially powerful for applications like real-time AR and scene reconstruction. But the trade-off is that each splat holds a lot more data than the typical vertex or point, and scenes often involve millions of them. Standard formats like PLY or OBJ weren't really designed for this kind of content, which is why we created SPZ, a format built specifically for storing, streaming, and rendering splats at scale. So let's go through what SPZ actually stores. So we have the positions, which are stored as 24-bit fixed point integers. So that's 3 bytes per axis, smaller than floats, but we still have tunable precision. There's rotations, 3 8-bit integers instead of full quaternions. We reconstruct the last component on the fly. The colors are standard 8-bit RGB, simple and pretty fast to decode. Scales are 8-bit log encoded, which gives us a large range at pretty small storage costs. Alphas are 8-bit unsigned integers, and spherical harmonics are 8-bit signed integers with enough precision for shading without bloating the size. Then all of this also gets compressed using libz for even more savings. So SPZ is quite simple by design. Everything is tightly packed, fixed size, and easy to parse. There's no schema negotiation, no optional fields. You know exactly what's in each splat and where to find it. And compared to more float-heavy formats like Ply, we often see like 70 to 90% smaller files. So the power in SPZ is in how little it tries to do and how well it does this one job, packing splats efficiently. So what does it look like in practice? So here we've rendered a splat from a very standard scene. On the left, the original splat. On the right, the same scene loaded from an SPZ, converted from the original. So pardon the jumpiness, we're only rendering the keyframe poses, not every frame from the input video. But as you can probably see, any differences between the two are practically imperceptible. And in this case, we've achieved over a 90% size reduction. So you might ask, how and why and how's that possible, I guess. And the full explanation is a bit technical, but the core idea is super simple. The bits of information we're not saving don't really add that much visual value to most scenes. And that's essentially the benefit of SPZ. The same fidelity, smaller files. So just as important as the format itself is how we've made SPZ easy to use, extend, and collaborate on. So SPZ is fully open source under the MIT license, so you can use it freely in any project, commercial or otherwise. We've really focused on keeping the code base minimal and approachable. So at its core, we're just 3 headers and 3 C++ files. There's very little setup. We didn't even have a build system to start with. And that simplicity has made it super simple for folks to jump in. And in the last couple of months, we've seen the community add a build system, fix like Windows compatibility and C++ 17 compatibility issues, a couple of other bug fixes, and it's been great. We've been collaborating a lot with contributors, and while seeing how quickly people are able to get up to and running inside our ecosystem has been super rewarding. On our side, we've also tried to add some features to help with interoperability, like tooling for coordinate system conversions, which is important in integrating with other rendering or authoring pipelines. So if you're curious, the project is small enough to probably read within an afternoon, and it's simple enough to contribute to without a bunch of infrastructure to set up. So there's a QR code on screen. We'd love for more folks to check it out and get involved. So we've made SPZ quite easy to use and extend through open source, but SPZ isn't actually a standalone format. It's already well integrated into some of our ecosystems, tools, and experiences. So we have a mobile app called Scaniverse that lets you capture real-world locations and build Gaussian splats entirely on device. So far, we have over 1.5 million splats created, and you could browse them today. We've also built some immersive viewing experiences. So we have Into the Scaniverse, which is a Meta Quest app and WebXR experience for exploring splats made by yourself and others in full VR. And finally, we really care about standards and interoperability. So we're working with other teams to bring SPZ support into glTF. We're also in the process of joining the Kronos group to help shape the future of 3D, like open 3D formats, and with a focus on ease of use and cross-platform compatibility. And well, lastly, SPZ isn't just something within our own ecosystem. Here are a few companies and tools that actually support the format already. And what's super encouraging in all of this is that these integrations came pretty much almost all from outside our team. It's just developers independently picking it up, understanding it quickly, and adapting it to their needs. So I think this kind of highlights some of SPZ's core strengths, right? We're simple, efficient, and super easy to integrate. So adoption's been growing. We see new users and contributors every month. And yeah, with that, I think I'd like to hand it over to Jason to talk a bit more about SPZ as a glTF extension.
All right, hello everyone. My name is Jason Sobotka. I'm a senior developer at Cesium Bentley Systems, and I'll be talking about our work creating a draft glTF extension for SPZ support and our current implementation within Cesium.js. This presentation builds a little bit, or is like something of a continuation of my presentation at the previous town hall, where we had a very simple prototype that was our earliest work with SPZ. So to start, just a high-level contextual overview of how we see the world and how we deal with data. We have our 3D tile format, which is our scene level. It's our open specification format for delivering and rendering geospatial content at scale. And within that, we have glTF, and specifically for today, Gaussian Splats. And when we deliver these formats, we want to be as small as possible, so we need some sort of compression. That's where SPZ comes in, and we want it to operate within glTF as best as possible. So why SPZ? Projit covered that quite well, but I wanted to talk about it from our perspective, and that it is open source. It's MIT licensed, which Cesium has always been open source minded and open source first. So that's very appealing to our ethos and how we approach solving software problems. And with that comes collaboration, which is always important. It was a great opportunity to collaborate with the newly formed Niantic Spatial versus just doing something within our own closed ecosystem or silo. This was just, we were covering the same ground as like, hey, we can work together and do something great. And the performance and simplicity. Like Projit said, it's a few files, it's easy to get up and running, and the compression is quite good for the simplicity that comes with it. This example here, 140 megabyte original file size down to 15 megabytes, and that's with all spherical harmonics. So that kind of compression is very appealing to us. So what does this extension actually look like? Also very simple. We take a SPZ buffer that's been generated from the library and map it into our glTF file. So you have your buffer, a buffer view within the extension, and then your attributes that it will then map into, which you have your position, your color, which is spherical harmonic 0 plus the opacity property. So we merge those into color 0. And then you have scale rotation. And then if you have them, your spherical harmonic degrees and coefficients. There's just a few listed here, but obviously there's many more that can be listed there. We decided to keep them separate. There's some discussion there, and this is something to iterate on. This is our first step, and you can use the QR code, follow the link. There's a PR open with an ongoing discussion, and we welcome feedback. So looking at the life cycle of an asset, if this looks simple, it's because it is. You have your PLI file that was generated from some piece of software. There's tons out there that will take your images and give you a PLI file. You encode that into SPZ, reference it into your glTF file, and then at runtime, decode it into your vertex attributes, and then render it however you see fit. There's no assumptions made as far as how you should render it or how it should be rendered. You just have your base properties and you can do as you please. And then we have our implementation. This represents a new pipeline versus the old one. If you saw the other presentation, or if you've pulled down the other branches, this is all new work for rendering splats within Cesium.js. We found all the problems using the existing pipelines, mostly with sorting and other issues. It's WebGL2 based. There is a Sandcastle example available. Again, there's a QR code in the link. You can download the branch, build it, and run it. I forget there's a video here. And this data here is tiled, showing that we're pulling down 3D tiles. It's tiled, and we're then sorting and rendering them as one asset. And I can do a live demo here. Let's see. So I'll just show that asset again. Just how quickly we can load and render assets at a geospatial scale on top of terrain, and then as also we have down here in the gallery at the bottom. This would be the demo asset you can go see now. So right, so what's next? We have our continued work on the draft extension. We're going to keep iterating. This isn't a final step or anything like that. And of course, our Cesium.js implementation will continue to improve and as we add features and improve performance. With that, I thank you for your time, and we'll take questions.
Thank you very much. Yes, we have some questions. Let's start with the first one. I think it's the first question is to first presenter, and this is what is the average PSNR loss examples of PSNR loss over various scenes as you measured? Maybe actually I'm confusing with the compression one, but just in case. And can this be tuned adaptive using the format features, which refers to SPZ?
Sorry, I don't think the first one was to us.
So basically, what the average errors that when you compress the SPZ, did you measure this?
I don't think I have numbers off the top of my head right now, but I'm happy to circle back and try to post them into the Discord afterwards.
Yes, cool. So the next question is
I can add a little bit to that one.
Sure.
In our previous presentation, we did do some numbers. The losses were minimal, and when you look at the baseline, the perception of those losses is basically imperceptible. It's minimal, and you really can't perceive the loss that's there.
Okay. So next question, is SPZ a format library or both? If a format, that what is the license for the format?
I mean, it's a format with a library to create and use it. We really want people to use it. I'm not sure of the exact technicalities in terms of the licensing. So again, I would circle back on that. But yes, it's free to use the libraries. We highly encourage people to use the tools and libraries that we have.
Okay. Does Cesium see the future of their ecosystem and 3D representation in 3D.js, or do they review this as a hybrid format together with a classic CG polygon-based approach?
Could you repeat that, the first part?
Yeah, does Cesium see the future of their ecosystem and 3D representation in 3D.js, or this is more like a hybrid evolution? So
We'll always be hybrid. The 3D tiles format is heterogeneous, and we'll always want to maintain that support. Gaussian splats are just one more tool in the toolbox for us to render geospatial content.
okay, great. So next question is, you mentioned you found it important to keep SPZ simple by keeping the set of parameters fixed. What are the implications when considered alongside some of the things mentioned in other presentations about, for example, additional lighting information channels or skeletons for animations?
So I think what we for now, we like to focus on solving the core problem, which is storing the splats themselves, and continuing to solve that efficiently and allow kind of an ecosystem to grow around this. So maybe through glTF and through other things. We do have some provisions probably within our reserve bits and other things to accommodate new features. And we're of course always developing in open source, so we'll evolve as the ecosystem evolves as well. But yes, I think we generally prefer for things to be built around solving and us continuing to solve the core problem of how to store splats efficiently.
Great. Next question is, why not use some compression there as standard at the moment, like mesh opt or ext mesh top compression and KTX2 and KCharp texture basis U? I think it's question to both of you. why you did invent NSPZ, and second, for Jason, why you're not using glTF ecosystem directly.
We did do some experiments with MeshOpt. I think overall, because SPZ is targeted more for splats, it was just a better fit for what we were trying to accomplish. And again, this extension is very early. Things can change. You know, like I said, it's not what's presented here is not in concrete. We want to make it as best as possible, and that's just going to come through, you know, feedback like this in iteration over time.
To add on, yeah, we also did experiments early on before developing SPZ of like using MeshOpt, Traco, other kinds of compression methods. And we sort of found SPZ to strike a good balance between being simple, being easy to use, and compressing greatly. So yeah, it experimentally felt validated.
Great, thanks. So next one, where does the name SPZ comes from, and what does it stand for?
The origins can make a guess. I think it was based on like splat zip because we use libz, so stuff like that. But I guess don't quote me necessarily on that.
Okay, let's keep some mystery behind this. Okay. The question to Cesium and Jason, what's the tiling strategy for splats? Will there be some LOD generation too?
That, in terms of LOD, that's ongoing work. That really has to happen on the training side, which we focused more on just the tiling and rendering side. It's a very hard, once the images are gone and you've done the training process, it's very difficult to just take a subset and build something that's cohesive. So that's definitely ongoing work in terms of LOD, but I think that solution is more on the training side, however that may take shape. Now, was there another part to that question?
Well, the tiling strategy in general, and second one, LOD.
Yeah, as far as strategy, right now we treat it just like a LiDAR point cloud, and we've had pretty good results with that. We've had to adjust some things, but overall, I mean, overall that's been kind of the core strategy so far.
Okay, and Jason, this next question is to you as well. How do you currently handle window borders in 3D tiles? Just some simple blending, or do you separate splats into windows based on ABBs or just centers? If so, is it sufficient?
Window borders?
Yes, I assume that's probably tile border or something, right? How you kind of combine the splats and integrate into the actual scene tree. I'm just making this up because it's not my question.
Yeah. That was one of the problems we had with the first implementation. We took it tile by tile, and it was great for performance because if you had a lot of tiles, you had a lot of concurrency, and it sorted pretty quickly. But then you couldn't actually blend the tiles together, which I think the first presentation talked about this a bit. Where in this new pipeline, we actually do this aggregation of the tiles, so we can do one global sort of the visible tile set and then render that. If that answers the question.
I hope so. And I'm not sure if it's for you, but probably for all the presenters, I have a couple of questions, super generic, so it's really hard to address to a specific one. Let's start with the first one. For CG-based content and CG model pipelines, what is the advantage for splats versus meshes? I believe we discussed this so many times, but I think it's never never hurt to repeat this again. And actually, I think, again, that's a question for all presenters. Really curious to hear your opinions on this.
Well, we can provide kind of a first answer. We wrote a little in the Q&A, but
You know, I feel like one of the reasons is that Gen AI seems to kind of fit better with Gaussian splatting. I've done experiments with Trellis where I give it the same image and ask it to produce a mesh and splats. And the splats are almost always significantly higher quality, I feel, for less resources. So yeah, I think things like fur, you know, hair, like semi kind of transparent stuff, it's much easier to model and get high quality using splats than you can with meshes. So I'm really excited to see what we can do with this once you kind of push the state of the art forward a little bit. Anybody else have any comments on this?
Yeah, I'll just say, at least from a geospatial context, you know, we're used to dealing with photogrammetry and, you know, generating meshes, and you bake your texture and all that. Splatting offers the ability to have, you know, you have your spherical harmonics. It's a little more of a dynamic result, and just another way to take that photogrammetry source data and render it. Yeah.
Great, thanks. Anyone else want to? Okay, so the next super generic question, in my opinion, is what do you think on newer GPU meshlets, which is some sort of in the spirit of Splats representation?
Sorry, did you say that was directed to me?
No, I think it's directed to all presenters as well. It's super generic.
I mean, I would think about those like as an extension also like to the previous question, right? I think like meshes are generally like fantastic representations, like triangles like make a lot of sense on the GPU. We understand them really well. We have hardware acceleration structures. For, you know, currently there's also like a lot of literature like exploring this like hybrid space, right? Like where we have like triangle-based splatting, etc., like going on there. I think that meshlets like also fit in there. I don't think there is like a right or wrong on either side in terms of like splats or meshes or meshlets or like other primitives, right? I think each has their space where they really, really shine. I think there is like spaces where meshes are just like the best thing that you can do. And these like intermediate representation are trying to like bridge the gap between a little bit and try to combine like advantages from some of these together, right? And so yeah, I think they're all exciting. Really, like it matters like what space you're looking at and what you want to do. And I think, yeah, just choose wisely from there.
Thank you very much. I think we can spend like maybe the next 3 minutes to wrap up Q&A, and that would be like well, the closing remarks. I still have some unanswered questions for previous presenters. Let me start with this one. I think it's to Wieland. What's your general approach to adjust the compression parameters?
Yeah, a lot of fiddling, I would guess, to get that right, and that's also why we started to build this tool so that you can experiment, you know, with the scene live, where you can try to find the best parameters for your particular scene. And as far as I'm aware, nothing like this exists yet, so you can do like larger runs, trying out like different hyperparameters, or you can yeah, set them to be somewhat working for your PSNR. So yeah, I think tooling is important in this regard, and so this is why we are building the tool so that you can explore the parameter space with live feedback on how that looks in your compressed data.
Okay, thank you very much. And that's another question. I see you already answered this, but again, we have like about 1 minute. So what about this compression, CUDA compression? What about the computational effort for compression, etc., etc.? So any kind of...
So the question was about the self-organizing Gaussians format. It maps the 3D Gaussians to a 2D grid. And the question was, so does this require CUDA? And is this something that takes too much computational effort to be in the way of, to be a barrier for most users? And I think it does not. So in our reference implementation, that was in PyTorch. So you can run that on CUDA. You can also run that on the CPU where it's slower. And so tests we've done internally, you can speed up this process by a lot to make this nearly instant on any GPU. And it's not CUDA bound at all. You can implement this in WebGPU or some other language. And I would expect any kind of user that deals with 3D.js to have a GPU. So no, I don't see this as a barrier at all.
Okay, thank you very much. And we kind of perfect in time. So Shannon, I will pass this to you to make this closing remarks.
Yeah, so just in closing, I wanted to say thank you to everybody for both to the presenters for sharing all of that awesome information with us, and to everybody who has joined. There will be a recording going up shortly that you can watch, or for anybody who wasn't able to join us in person, that they can watch. It'll be in the Metaverse Standards Forum videos. If we didn't get to discuss your particular question, or if you think of some questions later, please join us on the Discord channel so that we can keep the conversation going. Yeah, and I think that's oh, hey Patrick, I'll pass it over to you.
Hey folks, this is Patrick. I'm so sorry that I missed the intro there. I'm currently in Huntsville, so I was trying to translate Pacific time, the East Coast time, the Central time, and I had an off by 1 hour. So I'm really sorry about that, but I joined halfway through, and I'm really happy to see an awesome conversation. When we look at open standards, we're always thinking about, hey, what is the time to consider an open standard such that we don't fragment industry, except we're also able to continue innovation for a field that's moving fast, especially with the research community. So I just wanted to ask maybe our presenters, how do folks feel about the direction here with SPZ and glTF? Do we think that's a good area that we start considering as an open standard and still allows a lot of flexibility for all the innovation that's happening?
I guess as I talked about compression, I could give my view on this. So SPZ, so from a an academic point of view, is using a few of the tools that are good to compress, but is I think also leaving some of the tools we have to be most efficient on the table, and also from my point of view is somewhat limiting in what you're doing. So we heard it's a quite simple format, and it's always great. But also, yeah, how would you extend that, for example, for material properties is not quite clear to me. And yeah, from my point of view, yeah, the kind of formats we are working on that are image-based are super easy to decompress, because you just take an image and decompress it. This is also why people have been taking that up a lot, for example, in the Play Canvas engine. So yeah, I'm a bit critical of seeing some of the limitations of the SPZ format.
All right, well, thanks for sharing. Yeah, Leonard, do you have a response to that?
Well, not exactly response, more question, statement on your questions. And I know this is being actively worked on, but I can see two major areas of concerns within SPZ. One of them is for animation, and it's how do you deal with things as you try to animate pieces of it without actually having recorded that animation, so post-recording animation. And the second one is changes in lighting or mixing things that were potentially taken under two different lighting conditions. And Wieland alluded to the second one, and I think over the 3 town halls, there certainly has been quite a bit of discussion on the first one too. And from a more practical standpoint, I think there's a number of concerns or issues with the file format licensing and libraries. Exactly what is it before we can, we as a large community can jump in and say, yes, we're ready to go with that.
Okay, Leonard, thanks for sharing. Folks, other either reactions there or other perspectives?
Maybe coming from a biased perspective, maybe I can answer a little bit.
Please.
But I think it's important to sometimes remember to not always solve all the problems all at once immediately, like in the starting. It's okay to grow with the ecosystem. SPZ solves a certain set of problems, and I think when evaluating something like SPZ, what you want to do is to see whether it solves the problems that it's talking about. And as you grow the ecosystem into animation, into like 4D Gaussians, into other cool things that are going on, you want to grow these formats and you want to grow the tooling around them to support all of these things. So I would sort of keep that in mind while evaluating these kinds of things. And yes, we are MIT licensed. It is free to use for everybody. I think the format is also MIT licensed as such.
So Projit, I think that's all good points that you mentioned. And even when I look at mesh compression in glTF, we've had multiple parts of that journey with quantization and then Draco, then mesh shop. And I think each was appropriate at that stage of the ecosystem development. So I kind of would ask folks, hey, what's the alternative, right? If we don't maybe move forward with SPZ now, is it going to lead to additional fragmentation? It's actually going to be worse for us, as we bring these additional use cases or innovations. What do folks think?
So I'm not a speaker, but I'll speak for, I've been thinking about this at NVIDIA with some of the NVIDIA folks that have spoken today. There's a timing thing for sure, but it seems to me early. It's not that SPZ is wrong, but we should anticipate more changes. We've seen a lot of change in the last year. And one has to balance in figuring out when to double down and jump in and make a standard and put all that effort into saying, this is a standard and we're going to bake this into tools and software that ships. You have to balance that with the rate of change and guess the inflection point when change starts slowing down. And we start seeing that the cost and the time to make a standard matches the rate of change, such that the rate of change isn't too great. The risk is always that you get it too early and you have a thing that is no longer relevant. You heard, we all heard presentations about how fast compression is evolving. We heard about the emerging prevalence of dynamic, time varying behavior, skinability, material representation. All of those things, we don't know how that's going to fully converge. And there's a risk, therefore, that whoever does figure that out, well, it's highly likely that whoever does figure out how to get all that put together won't do it with a standard. They'll do it somehow. And then we're going to have to go update the standard several times. So anyway, that's where I'm at personally. It's not an official NVIDIA stance, but it's just, my thought. We have to be smart about judging the curve.
Indeed. Yeah, this is our third town hall, and every town hall has been about trying to have the community come together to tell us about that curve. So other thoughts, other agreement, or other perspectives? So folks, let me ask the alternative, right? If we don't, for example, consider something like SPZ now, what's going to happen with what everyone is doing in industry where they're all shipping products and they're all quite a bit different. Okay.
I'll take a stab at it.
Sure.
I guess your question in the previous, where you have the pragmatic real world scenario that software is already out there. They have to use a format. And so we're already seeing various formats emerging. They're solving, their own problems. And so it's already happening, whether we chase the research or not. There's still those products out there that are being used, and that there's an accretion that happens whether you want it to or not. So
I'll point out we can look at the history of image formats. If anybody remembers Image Magic. These days, many things can consume PDFs. We don't like doing it. It's horrible opening a PDF with not Adobe tools, but you can do it. So sometimes the people that consolidate businesses end up having an implicit format standard. But the image, Relong maintains an amazing repository that basically can import most anything. I imagine Forge probably will grow the ability to import a variety of things. Maybe that's another possible shape of the world as we embrace the fact that there are multiple formats, but we all get very good as a community of understanding how the formats differ and how they are similar, and that's okay for a little while.
And then before we go to Adam, yeah, I mean, I think that's a pretty interesting insight there. And I would imagine that I know there's many different image formats, but we would probably have far fewer splat formats. And then they're all different trade-offs. So like with glTF, there's Draco compression and mesh op. And one decodes faster than the other, one compresses better. And it's actually kind of nice that there's both. Adam, what did you want to share?
I would just like to kind of add on to kind of what you're saying, Nat, that like if you look at the image formats and you look at the history of the image formats and such, you're right. There have been a lot of them, and PDF I think is a particularly contentious one, because it was a document format that became an image format it's complicated. But what I kind of like to just, we need to remind ourselves that like, hey, if we start to look down the standardization route of one format now, that doesn't preclude us from doing something else slightly different later. And one of the things with like glTF in particular, and this is why like at Cesium we're huge fans of it, is that like just because today we're putting an SPZ buffer into that glTF doesn't mean that in the future, if there's a better way to store splats, then we can use that buffer instead, and we can have an extension that uses that buffer. And then, like, yeah, you'll still have to support two different formats because there's still going to be the SPZ stuff that's out there. That's the older stuff. But then you've got this new hotness over there that, 6 months, 12 months, 6 years from now, we know more about splats. And it's like we say, hey, you should use this one. But hey, this one you'll still have to implement. It's pretty easy. And I think that's one of the things that I just think that we all need to keep in mind right now. Just because we aim towards standardization of something now does not preclude us from standardizing something else later.
Yeah, I agree. Good point, Adam. Any reactions to that?
I would maybe like to make another point, which I don't see discussed so much. So where are we looking at the data? Like how what the compression ratios are, what the quality levels are. Has anybody like gathered a set of use cases and gathered a set of scenes from small to large, from in-house to inside to outside scenes, from geospatial stuff to synthetic web stuff, where we can actually properly compare the different methods and then select something that's appropriate there, and actually look at data of what the different methods bring there. I think that's should be very important in moving forward.
It would be awesome to see that. I mean, certainly Cesium has done some testing on the geospatial data. And then Projit, if I could put you on the spot, just because of how widely used SPZ is, do you have any comments there?
We've used it, we've tested it on a bunch of scenes, but I don't think we've done it on like these public data sets that Wieland has shared. And that would be a great next step to probably try out.
So folks, I know I'm taking us a few minutes over, but I do think this is a key conversation right around that, as Nat said, that kind of where are we on the curve? Is there a subset that we think makes sense for standardization to prevent fragmentation, knowing that additional standards could come as we look at other compression and animation and so on. So just looking for, any other perspectives or anything that someone would want to reiterate that they've heard.
There's some comments in the chat too, Patrick, part of the conversation.
Yeah, so I see it.
While we parse that, I might say I agreed with the points I heard about, like, I almost heard what was said as if we're careful about a market segment or a set of use cases, that determines a V1 or a revision or a target thing. You know, if I said TIFF to all of you, do y'all remember when that was common for scanners? Right? It quartered that market. It did a good job. So there might be a way to think about it in those terms. This will be the set of use cases we care a great deal about, and we'll do a good job at that set of use cases for that market segment. We'll make the thing synonymous with that generation. And of course, there'll be things that come later. But that way, you also draw a box around what we want to do really well that works today from the things that we know don't work today. And that's why there's research, but we're not caring about that. Right. And so, for example, you know, Patrick and many people have mentioned geospatial, and like there, it's great, is my impression. So great. That's in the current V1 box potentially more viably than, say, reconstruction of you know, shiny cars that are moving in a dynamically lit environment.
Yeah, good summary, Nat. Shannon?
Yeah, I kind of want to sidecar onto that to mention everybody's favorite topic in standards, which is naming. But I think that, you know, it was something that Projit said was so there's this thing that we know how to do well, and that's, you know, the representation of the Gaussian splats themselves. But I think that there's some ambiguity in what Gaussian splats means. Like, is it inclusive of dynamic splats? Is it inclusive of relightable splats? So I think we need to be careful about saying, like, okay, here is a containment method for simple geometry, or you know, and explicitly state, like, here are the not yet defined pieces.
Yeah, the naming and the vocab is so important in computer science as a whole. And actually, if you look at the current proposed extension, I think it's very clear that it is SPZ, the Gaussian splat compression, right? So it's like, hey, this is the subset that it focuses on. Interesting. Reactions to Shannon's comment? Cool. Other comments? I mean, basically what I'm hearing here is, you know, yeah, I think it could make sense to say that we might standardize on some of the subset of today's use cases and today's solution to avoid fragmentation, knowing that there's likely generations coming that will solve, you know, again, maybe more compression or animation. Is that maybe a fair summary? Any disagreement with that or other perspectives? Okay, cool. Shannon, I'm sorry I took us 15 minutes over on the wrap up. Would you like to wrap us up again with any of the calls to action, how to get involved in the forum?
Sure. Yeah. Just reminding everybody. So I think actually I've seen a couple mentions in the chat sidebar that the Discord link might not have been working for some folks. So I wanted to check if we had double checked our link and made sure that it is still a live invite. I can't tell because I'm already joined to it. So okay. Lassie just posted the permanent join link. So yes, please join us on the Discord and follow the, you know, stay in the conversation as we continue to talk about this. Thank you once again to all of the presenters and everybody who has joined. This has been an absolutely fascinating discussion, and I look forward to it continuing on Discord.